Hi folks, my name is Michael and I'm going to be talking about the secure SDLC. And if you don't know what that is, you're in the right spot. So, Alt-Tab? Oh. All right, so I'm going to start off with a quick question. Raise your hand if you've ever used a car key before. So like a remote car key fob, press the button, it opens. Okay, so pretty much everybody, if you own a car, you probably have used this. Even if you haven't owned a car, you probably use this. Have you ever thought about how that system works?
Radio signals.
Radio signals, that's one answer. Any more than that? I know you do, Kenny. RFID is definitely radio.
Pre-programmed codes that connect the keys to a specific time.
Yes, there are pre-programmed codes that... Okay, so why would you need that?
You need that so that you don't have one car key that can unlock every car from a specific.
Right, so you would need the key to have a unique key, actually, a unique code of some kind. So let's take a look at how this would work in practice through this expert drawing here. On the left side, we have you with your car key. And so you press this button, and this is our very basic protocol, where it sends a secret code to the car. And your car makes a decision. It says, okay, is this the code that I have on file? And if it is, then it opens the door for you, and you can maybe start the car or something like that. Sounds really good, right? Well, let's consider an alternative scenario. You send your key to your car, and Eve is in the middle, and Eve actually saves that because it's radio, and you can just, receive that signal. And, well, the good news is that your code is still the same, so you still get into your car. The bad news is that Eve also has your code. And so Eve can do what's called a replay attack. And Eve can send that secret code to the car and then actually open the car too. So two people with the same car. Long story short, Eve steals your car. And this is not a good scenario, right? This is the kind of moment where you start to think about, why did this happen? Well, it's a very common attack when you have a very not well-designed cryptographic protocol like this. So this is something you should think about. And you start wondering, when could we have thought about this? How could we have prevented this catastrophe? Because remember, this is a car key fob. And many, many cars will be out there on the market, and they'll be vulnerable to the same attack. And so you can try and recall the car or something like that. You might be thinking this is just a hardware problem. It is also a software problem. Let's say you're running a website, and that website gives out coupons, and you find out later that those coupons are predictable or guessable in some way. Well, that's a problem too, because then you have to avoid coupons, and no one likes that. When you make errors like this that are hard to recall and hard to fix, it comes with a lot of additional cost. So let's consider how software is developed and how we got to this position here. Raise your hand if you've seen a document or a diagram like this. Maybe you've seen this in one of your courses or in a very old PowerPoint. And this is basically a diagram that would describe how a software component is created. And so this starts at the very top with your requirements. It's very old school waterfall method. You go through your design, your implementation. That's when you actually create the code after you've created that design. And then you verify that it works, some kind of testing component to make sure that what you wanted to build is what you actually built. And then after that, you maintain that project for however long that your stakeholders need it. And so this is called the software development lifecycle. There are many different kinds of SDLCs. They might have 6 steps or 7 or 8, but it all sort of boils down to the same routine. You create some idea, you have some problem that you want to solve, you design a solution for that, you implement it, verify that it works, hopefully, and at the very least maintain it until it's no longer needed. Does anyone notice anything that we're missing here? Any part that would help in this scenario?
Security.
Yeah, so there's no the S in here stands for security. There's no security in this diagram. Maybe you might be thinking, well, it could happen in verification, but verification's really just for verifying that the design is actually implemented. You could verify a whole bunch of things, but the amount of security attacks out there are, they're not going to be able to come up with probably all of them after the fact. And so you end up with a problem where you have many, many, many potential attack vectors, many people that are trying to attack your system, and very few defenses. Not a spot you want to be in. And so you really want to have something better than this. And most software, these days that's regulated, especially is going to have a better model than this. We need something that will scale to this need, that will address these concerns. So we're going to introduce some security testing. So if you've never heard of the secure SDLC, it basically has a couple of different characteristics. You might have heard these other acronyms. You might see them later. SAS and DAST are static and dynamic application security testing. So this is dealing with your actual application code, making sure that what it calls, what it takes for input, is handled correctly. These are often automated testing suites, and so whether they're really revolutionary or an old copy of Nessus is for you to find out when they inevitably fail, but they are sworn to by many organizations around the world. They do catch the low-hanging fruit, and for that, it often justifies the price of admission. Modern software is increasingly complex. There are many, many, many different dependencies. If you've written any JavaScript in the past few years, you'll probably know what I'm talking about. There are just tons and tons of dependencies in a modern application. Transitive dependencies, you have to deal with updates, so when vulnerabilities are discovered or just new features are added, how to handle those updates without breaking the stability or security of your application. There are so many different potential scenarios that can go wrong when you handle dependencies incorrectly. Many of these issues have been solved by better package managers, but there is still always this problem of dealing with trust. You have to trust who you're depending on. Additionally, you'll hear maybe in Black Team or other areas of the industry for sure, this idea of infrastructure as code. And so in the tech sector, for the most part, and growing in general with technology, we're seeing a lot of organizations stop dealing with sitebooks and special configuration done by hand and moving towards an infrastructure as code solution. This comes with a lot of the same problems of writing any kind of code where you can make errors and have those be committed and automatically and very quickly deployed. And so when you deal with an SDLC, you'll want to consider both the security of your application and of your deployment. And another topic, or at least another catchphrase you'll hear about sometimes in the context of testing, maybe of security, is this idea of shifting left. And so you'll hear about this maybe from a lot of larger tech companies, this idea. And we'll talk a little bit about what that means. But generally speaking, we're talking about doing testing earlier. And so this is a very grainy diagram. I couldn't find a better diagram, but it talks about all the things that we need to talk about. And so on the left side of this V up here, from the top to the bottom, we can see a similar model to what we showed before. We're starting with the needs of the user. What does this software need to solve? What problem is here? We want to be able to openly or remotely open our car, for instance. That would be our user need. Our requirements, it needs to be easy to use. It needs to be something that can fit in your pocket. It needs to have a battery that lasts more than a couple of hours. And that leads into your systems engineering, all the different subsystems in that. How do you architect that piece of software or hardware so that it runs at a usable performance and stuff like that? You want good design so that it's easy to extend. And eventually you come up with some kind of implementation at a hardware or software layer. On the right side, with arrows pointing, validating or verifying each step is the kind of testing that you would use for that component. So code is written in, you have units of code, and you'll use unit testing to verify that those units work individually. You'll combine those units into a subsystem for integration testing. This is when you take a piece of software and you actually see if it works. You put all the parts together and actually run it. That's for one subsystem. You might have many comprising a larger thing. And that goes up the stack until you talk about acceptance testing. Basically, does this match our design? Does this actually do what we want it to do? And finally, if you're doing the right thing, you'll probably talk to your actual users and say, hey, does this actually work for you? Does this do what you need it to do? Does the insulin come out when you push the button, et cetera? So these are all things that you need to pay attention to when you're designing software that's meant to last. And the idea of shifting left is that basically, instead of waiting till the very, very end, when the car is already released and people can hack into it, you start caring about these things as soon as you start thinking about requirements. So here's how this is going to benefit an organization. This is why so many organizations are talking about a secure software development lifecycle. One big benefit is that bugs are fixed earlier. You start thinking about your issues before they happen. You start thinking about how the inputs to your system can be used and abused by malicious actors. And you start developing countermeasures at every layer of the stack. And because you're fixing things earlier, in the lab, you're saving a lot of money too, because you're not having to release updates that might cause downtime. You're not having to recall a whole bunch of hardware. This is very, very, very important when you start dealing with any kind of software that's not just like, a social network or something, things that need to run all the time, real-time, operating systems, healthcare stuff. These are all things that you really need to think about when it comes to security, and this helps you reduce the cost of issues when they come up. And the other benefit that you get that's sort of transitive with this is this idea of defense in depth. Raise your hand if you've heard of defense in depth. Okay. Does anyone want to tell me what it is? Malik.
All right. So defensive depth is that when you kind of get concept of security through obscurity, so you focus on the tiny details and secure the details of your code instead of having like firewalls only.
Yeah. Okay. So the answer there basically being that you focus on the details instead of just having one perimeter. You build a moat and you hope that no one gets past it, and you make that really tall moat or whatever, wall or whatever you want to call that. The idea with defense in depth is that you have many layers to your system, right? And so we try and protect those layers individually. And the benefit of that, you can think of this when we talk about, you can think of this as like a Swiss cheese model. This is a very common, mnemonic basically. When COVID happened, there were a lot of Swiss cheese models about how we deal with COVID. And ultimately, all that boils down to, in formal terms, is this idea of defense in depth. You have different layers of your stack, different protections, many of them are a little bit smaller, but robust enough. And so the idea is that whatever you're trying to protect against, maybe it gets through a few, but it doesn't get to the other end, to your user data, towards disaster, towards Eve stealing your car. And so in our example, we would probably consider this idea of a replay attack well before we implement our protocol. We'd be thinking about how we create this securely. We'd do some Googling for a couple of minutes. Maybe we hire some actual cryptographers to do our cryptography, and then we'd catch this before we implement it and ship it out and have people hit the road with it, quite literally. So this idea of a secure SDLC, we've talked about this diagram. Here's a different kind of diagram, and I think a better one to realize how modern development works. On the left side, the left circle is the cycle of development, basically creating applications, and on the right side is operations, actually deploying them securely. And looped around all of them is a consistent and constant security process, both when you start in the middle with planning a piece of software or planning any kind of system, going all the way around testing, building, releasing, deploying, and then eventually monitoring and maybe deprecating that service eventually when you don't need it. So this is from GetGuardian, and it's this is a very common thing that you'll see here. The idea, of course, with the outside perimeter is that we're not creating just a simple outside perimeter like you would in a firewall scenario, but rather implementing security through each and every step of your development process. So what are some things that you would actually need to do to implement this? We've talked about some diagrams, we've talked about some buzzwords. We can talk a little bit about how these actual practices are implemented. So the first thing that you want to do is you want to start thinking about your risk management before you actually create an application. And so when you talk about what this needs to do and what this is going to be built on and what sorts of people are going to be involved, you're going to start thinking about ways that can go wrong immediately. This is kind of hard to convince people to do, but in the long run, when you're dealing with very sensitive systems, systems that require high security, that require high availability, you'll start to think about these kinds of massive issues, especially when it comes to very large organizations that frankly have been through them before. They'll have some war stories to tell you about the ways that things can go wrong. And so the healthy thing to do is to channel that into your risk management process and have that be a history piece instead of a current problem. And so you're doing this well before the actual code is designed, just to be really clear about that. When you're starting to think about, let's say, your social network, maybe you think about some of the features on that social network, and from a trust and safety perspective, maybe how they might be abused. This is a common thing now after the fact, but many of the social networks that we use today did not consider these when they came out. And so the problems that have arisen from governance for that sector have been kind of contentious. When it comes to software or hardware modules, there are different kinds of problems, but the risk is still the same, at least in the way that it's managed. You want to be ahead of the game. Additionally, you're going to start by defining trust boundaries. So this is a concept in computer security. You have data coming in and data coming out. You have permission levels, and those represent trust boundaries. So if you picture, let's say, a web application that takes in user input, that input box or whatever is some kind of trust boundary, basically. you're taking in information that is not trusted. You have to sanitize it. You have to handle it in some way. You have to make sure that people aren't doing cross-site scripting and all that stuff. So that's an example of a trust boundary. Another trust boundary is your root permissions on Linux. So crossing into root permissions from a regular user, an unprivileged user, would also be a trust boundary. You want to have a really clear idea of that before you get into things, so that you can both anticipate the kinds of attacks that are common, but also think about potential future issues that could come from the access or privileges that you're giving out with your service. And the other thing too is to try and invest in secure coding training. We've come a really, really long way in creating developer APIs that incentivize security, that are secured by default, and that developers frankly don't have to think about. Anyone who's done PHP for a while will probably know what I'm talking about. If you're running any kind of organization, if you have the funds to do it, or you can at least take some time to think about these things, it's really, really important to get everybody that's actually developing the system on board with security. You don't want them to think that this is a hassle or a cost center, or else corners will be cut and Eve will steer your car. You're also going to want to automate the testing, auditing, and deployments. So when you test the software, it should be really easy, quick, and not inexpensive to operate. I've seen Discord bots that require it to connect to Discord to test. I've seen cryptocurrency stuff that requires actual cryptocurrency to test. That's literally expensive. You don't want to have any kind of cost with your testing, so you want to design it with a very low cost. Your auditing should also be as automated as possible. When someone creates, let's say, a resource, maybe you want to check the actual permissions on that resource when it's created, not 10 months later when you have a data breach. And additionally, your deployments should also have a certain amount of automation to them. You don't want them to be done by a single person who can fat finger a button and take down BGP or something like that, which has of course never happened. And ultimately what this means in practice is you're going to have infrastructure, detection, and policy as code. There are different platforms that offer this, different companies, startups, et cetera, open source projects. But the general idea is that if you do things in code, it's just text. You can handle that on Git repositories. You can collaborate on pull requests to that policy and change things really easily without blindsiding other people on your team. So for instance, if you have a firewall, maybe you want to manage your firewall rules through a Git repo so that way when people change them, it's really obvious. You do have a pull request. Everybody knows about it. You can comment, discuss in that pull request on different ways you want to change things, the outcomes of that change. Makes it really, really easy to centralize your deployments, centralize all of your discussions about this in one spot so that people are not surprised when things change. The ultimate goal with the secure SDLC, in order to get it in your organization, in order to get people to get on board with it, you have to let automation actually accelerate your security, basically so that your developers get on board and it doesn't slow them down. The idea is that you want to incentivize security so that people actually feel good about making things secure, that they feel like they're contributing to the overall product. You want to incentivize that, and a good way to incentivize that and reduce the hardships is to really embrace automation. And so that's basically the secure SDLC. It's basically a standard or good practices that you can implement at every layer of your development to actually secure things in practice. And I'm happy to take any questions. You can do just about anything. Kenny? Really? Okay, all right. Anyone else? Okay, Kenny. What was your question? No, really, we're all waiting. Yeah.
How do you look like that? And it's like what? It looks so good. Good job, Michael.
Thank you, Kenny. Thank you, Kenny. I love you, Kenny. Love you, Kenny. But yeah, thanks. I appreciate it. And yeah, if you guys have any questions about this kind of topic, this is sort of like a high-level overview of different practices you could put in. Not a super technical thing, but if you're working somewhere where they're not doing testing or security or whatever, maybe bring this up. That's basically the gist.